In our last video, we introduced the concept of a vector field. Function assigns a vector to each point in its domain. Really quick before we draw some pictures here, sometimes we'll talk about continuous vector fields or differentiable vector fields. We define a vector field to be continuous or differentiable if the underlying functions, the component functions here, like this, all are continuous or all are differentiable. So we'll just refer back to previous definitions for that. I'm writing this out for a 3D vector field. Of course, if we were working with a vector field in the plane, you get rid of this and you get rid of the z components. Those would be our definitions there. Okay, let's draw a picture here. So one powerful thing about vector fields is that we should think about what their pictures look like and what their pictures tell us. So sketch the vector field. This is going to be a vector field on the plane. F is equal to -y, comma, x plus y. And so how do we go about doing this? Well, we should just compute our vector field at several points here. So f of 0, comma 0. Let's see. So associated to the point 0, 0, -0, comma 0 plus 0. Okay, so the 0 vector gets associated to the origin. F of 1, comma 0. Let's see here. So we would associate that with -0, 0, 1 plus 0 is 1. So the point 1, comma 0 gets associated to the vector 0, comma 1. F of 1, 1 is going to be associated to that -1. And then 1 plus 1 is 2. And so then we would keep, what we would do here is keep making a chart of lots of these, and then we would, what vector gets associated to each point, and then we sketch them. That's a little bit of a tedious exercise to do in a video, so I just went ahead and, so for f of x, y is -y, x plus y. I just went ahead and graphed, did that for a bunch of points here and plotted it. So f of 0, 0, 0, 0, the 0 vector, I can't really draw the 0 vector very well. F of 1, 0 is 0, 1. F of 1, 1 is -1, 2. You can keep reading off as many of them as you want to. For example, f of 0, comma -1 is 1, -1. Okay, so this is a picture of a vector field. Some points to make here. So number one, the scale in some sense does definitely matter here. So this vector and this vector, these are going to be parallel vectors, but I'm intentionally drawing this one. It's supposed to be twice as long as this one. It's probably a little bit more than twice as long, but there definitely is something to it that this vector is longer than this vector. I want to try to draw that, represent that accurately when I draw that. Of course, I should emphasize that I'm only drawing the vector field at select points in space. I'm only drawing it at some of the points of the unit lattice where x and y are both integers. So of course, really we should be thinking of this vector field as associating a vector to every single point, including something like, x is 0.56723 and y is -0.4327 here. We just can't show every single vector on here because then the whole thing would be a mess. So having this picture in mind, being able to go from this to this is important. I should emphasize that when we draw vector fields, we draw them so that the tail is coming from the point in question. So at the point 1, comma 0, we are drawing the vector 0, comma 1. And so we're starting, the tail is at 1, 0, and then it goes away from the point. Okay, so we should be able to, draw this kind of picture. Obviously, drawing a three-dimensional vector field would be a lot more difficult. But also in future sections, we'll think about, we'll have functions of vector fields, and those functions will tell us certain things about the vector field. For example, this right here, there is some kind of maybe circular behavior going on. That seems like that we are rotating around here. So like if we're rotating in a counterclockwise direction. Like we're at this point we're heading down, or at this point we're heading, down and to the right. If we're over here, we're moving to the right. So there's some kind of counterclockwise movement. We also are in some ways moving away from the origin, that like if we're here, we're moving farther away from the origin. We're here, we're moving farther away from the origin. We're here, we're moving farther away from the origin. So in future sections we'll be, there will be, in future sections we'll have functions that kind of capture what it means to rotate counterclockwise, rotate clockwise, things that capture rotating, moving away from the origin, or moving away from the point in question. We'll be talking about that in future sections. One more thing to do before we wrap up this video. I do want to point out that this is actually not the first time that we've seen vector fields in this class. So if you remember the chart that I've made, I'm making it sound like, this is a brand new thing that we're doing here in chapter 16. We've actually have already seen an example of a vector field without calling it a vector field. And so this is back in chapter 14, but the gradient function is a vector field. So, for example, if we have f of x, y, z is the function x squared y plus xz, we know that the gradient of f is, the x partial derivative is 2xy plus z, the y partial derivative is x squared, the z partial derivative is x. And so this is a vector field. This right here is a vector field. For each point in space, of each point here in R3, we're associating a vector to it. So the gradient f evaluated at a point x is 1, y is 0, z is 2, is going to be the vector 2 times 1 times 0 plus 2 is 2, 1 squared, 1. So it associates the vector 2, 1, 1 to the point 0, 1, 2. The gradient function gives us a vector field. And in fact, gradient fields, I'll start saying gradient field a little bit here. Gradient field are some of our most important examples of vector fields. Okay, so this is all good. We have better intuition for what's going on here with vector fields. We're getting closer to defining vector of line integrals, because that's where we're headed in this section.